Diffraction is the bending of light waves around the edges of an obstacle. The phenomenon of bending of light around the corners of the obstacle and spreading of light waves into the geometrical shadow region of an object placed in the path of the light is called diffraction. The best example of diffraction is colors observed in peacock feathers, colors observed in halogram. In Young's double-slit experiment, interference of light is due to bending of light at two slits of there is no bending at the slits, there is no possibilities of interference. So diffraction is common characteristic property of all types of waves or propagates the wave. So it has to bend around the corners of the obstacle placed in the path. Because of its extremely shorter wavelength, such bending is pronounced and hence light appears to travel in the straight line. The diffraction effects are obtained and are observable only when the dimensions of obstacles are comparable with the wavelength of the waves concerned. The main causes of diffraction is limiting of wave front by an obstacle or an aperture. So conditions to observe the diffraction: if the size of the obstacle is much longer than the wavelength of light, then it appears the light advances by a rectilinear propagation. If the size of the obstacle is comparable with the wavelength of the light bends around the corners of the obstacle and spread out into the geometrical shadow region. So what is the Huygens principle? Every point of the source is a source of a secondary wavelet. If the diffraction phenomena was explained on the basis of this theory, according to Huygens theory, every point on the primary wavefront acts as secondary sources of a distribution or disturbance, and stationary waves are generated from the points. To envelope of these secondary waves forms secondary wavefronts from the diagrams. So what is the difference between Fresnel and Fraunhofer diffraction? And Fresnel and Fraunhofer diffraction, the Fresnel diffraction is, for diffraction to occur, the light source and the screen both are finite distance from the obstacle. And Fresnel diffraction, to study the lenses are necessary, lenses are not necessary. And Fresnel diffraction, the incident wavefront is either spherical or cylindrical shape. The Fresnel diffraction can be studied only in the direction of the propagation of light. The study of diffraction is complicated in Fresnel. In Fraunhofer diffraction, the light source and screen both are finite distance, infinity distance from the obstacle. The study of diffraction, lenses are used to study the diffraction. The incident wavefront is considered as plane wavefronts. Diffraction can be studied in any direction of the propagation. And the study of diffraction is very easy in Fraunhofer diffraction. So there is a very difference between Fresnel and Fraunhofer diffraction. Fraunhofer diffraction due to single slit experiment. So in the diagram, it is a plane wavelets WW dash. AB is a slit system, and OP0 is called directed to the light beam passes to the OP0 on the screen. OP1 is called the maximum minimum intensities. In Fraunhofer diffraction, the incident wavefront must be plane waves. Let us consider a slit of width is small e. Let the plane wavefront WW dash of monochromatic light of wavelength propagating normally towards the slit is incident on it. The diffracted light through the slit is focused by lenses of convex on a screen placed in the focal plane of the lens. According to Huygens-Fresnel, every point of the wavefront is the plane of the slit is the source of secondary wavelets, which is spread out all the directions. These wavelets traveling normal to the slit system along the direction is OP naught are brought together focused at a point is P1 by the lens. Thus P naught is a bright central maxima. The secondary wavelets traveling at an angle theta with the normal are focused at a point P1 on the screen. Depending on the path difference, the point P1 may have maxima or minima intensities. To find the intensity at P1, let's draw the normal AC from A to the light ray at B. The path difference between the wavelets from A and B in the direction theta is given by the path difference is equal according to triangle. So from the diagram is it is called the slit system. It is called the OP naught in the screen, bright central maxima, and this is called the wavelet. This is called the diagram. That is called slit is called AB slit. So this one. So this is called C. So BC is equal AB sine theta. BC is equal AB sine theta. Width of the slit is small e sine theta. So the corresponding the phase difference is equal to 2 pi by lambda into path difference. That is 2 pi by lambda e sine theta. That is equation 1. From the diagram is as shown in the figure. So the AB is called the width of the slit small e, and C is called an angle is the opposite side. That is called BC is equal to AB sine theta. From the diagram, that the width of the slit is divided into n equal parts, and the amplitude of the wave from each part is A, and each part will be the width is called width of E by n. The phase difference between any two waves from these parts will be 2 pi by lambda E by n sine theta is equal 1 by n. 2 pi by lambda E sine theta is equal D. That is called the phase difference. The width of the slit is the same. Then the amplitude will be also same. Using the vector addition method of the amplitude, R is given by R is equal to A sine n d by 2 by sine d by 2. And equation 1 from equation 2, R is equal to A sine pi e sine theta by lambda sine pi e sine theta by n lambda. And simplification is R is equal to A sine alpha by sine alpha by n, where alpha is equal to pi e sine theta by lambda. That is R is equal to A sine alpha by n. Alpha by n is a small value when compared to the alpha by n. That is called the sine alpha by n is equal to alpha by n. So where R is equal to n a sine alpha by alpha, n into a is the number of width of the slit, and a is equal to each slit of the amplitude. That is the total amplitude is capital A. Na is equal to a sine alpha by alpha. Therefore, R is equal to A sine alpha by alpha. That is equation 3. N tends to alpha and A tends to 0. Then Na is equal to A. That is a finite value. Therefore, the resultant intensity I is equal to R square is equal to A square sine square alpha by alpha square. That is called the maximum intensity. Maximum intensity. So then you'll find that three conditions: principal maxima, minimum intensity position, and secondary maxima. The first one is principal maxima. The principal maximum is intensity will be maximum, resultant amplitude also maximum. From the equation 3, the resultant amplitude R can be written as the ascending power of alpha. Then R is equal to A sine alpha by alpha. A by alpha into sine alpha, that sine alpha is the ascending power of alpha. Alpha minus alpha 4 3 by 3 factorial plus alpha 4 5 by 5 factorial minus alpha 4 7 by 7 factorial plus and so on values. Alpha is a common value. Alpha cancel. Then the intensity I will be maximum. Then R will be maximum. The maximum value R negative in terms of the vanishes. Alpha is equal to 0. Alpha is a value of phi e sine theta by lambda is equal to 0. Is equal to 0. either lambda is equal 0, pi is equal 0, sin theta is equal 0. Sin theta is equal 0, theta is equal plus or minus n by. Then r is equal to a. Then I maximum is equal to r square is equal to a square. That is called the maximum condition. If the condition theta is equal to 0 means the maximum intensity is focused at a P naught. The P naught is a bright central maxima or principal maxima. And second one is a minimum intensity condition. The minimum intensity condition I will be minimum, then R will be minimum. R is equal to A sin alpha by alpha is equal to 0. Either A is equal to 0, R is equal to 0, sin alpha is equal to 0. Sin alpha is equal to 0, alpha is equal to plus pi, plus or minus n pi. So n is equal to 1, 2, 3 and so on. Substitute alpha is equal to plus or minus pi plus or minus 2 pi plus or minus 3 pi and so on values. Where alpha is equal to plus or minus m pi, where m is equal to 1, 2, 3 and so on values. Here alpha is equal to 0 indicate the principal maxima. Then pi e sin theta by lambda is equal to plus or minus m pi. Both sides pi get cancelled. Then e sin theta is equal to plus or minus m lambda. E sin theta is equal to plus or minus m lambda. The point P1 will be minimum intensity of the value of theta satisfying equation 7. And we obtain the points of the points minimum intensity present on the sides of the P naught. Either sides of the P naught means it is called the either sides of the principal maxima, that is called minimum intensity position. Another one is secondary maxima. In secondary maxima, the addition to the principal maxima with alpha is equal to 0. We observe there are weak secondary maxima between any two minimas. The position of these maxima can be found from the condition for maxima of a function. The position can be obtained by the differentiating with respect to intensity with respect to alpha and equating 0. That is di by d alpha is equal to 0. That means differentiation the intensity with respect to alpha and equating to 0. That implies d by d alpha into a square sin square alpha by alpha square is equal to 0. So a square is a constant value removed from the differentiation. A square d by d alpha into sin square alpha by alpha square is equal to 0. That is called a differentiation of the equation. And finally simplification. A square is equal to alpha square 2 sin alpha cos alpha minus sin square alpha 2 alpha by alpha 4 is equal to 0. That is a square sin 2 alpha sin alpha alpha cos alpha minus sin alpha by alpha 4 is equal to 0. That is a square is equal to 0. Either 2 sin alpha is equal to 0, alpha or 3 is equal to 0, alpha cos alpha is equal to 0. That means sin alpha not equal to 0, alpha not equal to 0, alpha cos alpha minus sin alpha is equal to 0. Hence the position of the secondary maxima are given by alpha is equal to tan alpha, y is equal to alpha, and y is equal to tan alpha graph is as shown in the figure. From the values of satisfying the above equation, we obtain the graphically by plotting the two curves y is equal to alpha and y is equal to tan alpha on the same graph. The position of intersection of these two curves gives the values of the alpha which satisfy the above equation. So that is called the representation diagram. 0, pi by 2, 3 pi by 2, 5 pi by 2 and so on values. And here 0, this is called pi, this is called 2 pi. Another one is this is called minus pi, minus 2 pi and so on values. So these points or intersections is alpha is equal to plus or minus 3 pi by 2 plus or minus 7 pi by 2 plus or minus and so on values. Substitute in the equation and differential equation in the respect of alpha. Alpha is equal to 0, I naught is equal to a square principal maxima, and alpha is equal to 3 pi by 2. I1 is equal to a square sin square 3 pi by 2 by 3 pi by 2 square is equal to a square by 22. That is the first secondary maxima. And alpha is equal to 5 pi by 2. The place of alpha we substitute 5 pi by 2, that is called a square by 62, the second secondary maxima. So this is called intensity distribution curve. So 0, pi. Pi means the curve is called in the ground level, touch the here, that is called the minimum intensity positions. This is called minimum intensity positions. And this is called first secondary maxima, second secondary maxima, third secondary maxima. Gradually it is decreasing. So from the above equation, it is clear that the most of the incident light is constructed in the principal's maxima and rest in distributed as secondary maximas. So the intensity distribution curve, like this one, the intensity distribution curve is as usual in the same. So 0, pi, plus or minus m pi, and alpha is equal 3 pi by 2 plus or minus 3 pi by 2 plus or minus 5 pi by 2 plus or minus 7 pi by 2 and so on. That is called first secondary maxima and second secondary maxima. So this is called Fraunhofer due to single slit. The another one is the Fraunhofer diffraction due to double slit experiment. So here in the double slit experiment, the two slits is there. S1 and S2 is the double slits of equal width is small e and separated by the distance is small d. The distance between the middle point of the two slits is E plus D. Here that is called E plus D. And let a monochromatic light of wavelength lambda incident normally on the two slits. The light diffracts. The light diffracts from these slits are focused by lens on the screen. The diffraction at the two slits is a combination of diffraction as well as interference. That is, the pattern on the screen is a diffraction pattern due to single slit on which the system of interference fringes are superimposed. So from this diagram is the maximum minimum conditions can be calculated using the path difference between the two diffracted rays from these different coherent sources. From the path differences of the above diagram, the path differences that is called path differences S1, S2. This is S2K. This is called S2, S1K from the diagram. So the path difference S2K is equal to E plus D, S1, S2 sine theta. S1, S2 is E plus D, E plus D sine theta. And phase difference is delta is equal to 2 pi by lambda into E plus D sine theta. So the resultant amplitude at P1 can be calculated by using vector addition method, in which two sides of the triangles are represented by the amplitude. So this is called one slit of amplitude. The resultant amplitude R is equal to A sine alpha by alpha. Another slit of the resultant amplitude is A sine alpha by alpha. This is called the total resultant intensity. So the total resultant intensity according to trigonometric function, triangles are represented by the amplitude through the two slits. So according to OH square is equal to OG square plus GH square plus 2OG into GH cos delta. So OG value, GH value, and the value substitution simplification, R square is equal to A sine alpha by alpha whole square, A sine alpha by alpha whole square, 2 into A sine alpha by alpha, A sine alpha by alpha cos delta. So it is called common value A 2A square sine alpha by alpha common 1 plus cos delta. That is R square is equal to A square sine square alpha by alpha square 2 cos square delta by 2. R square is equal to 4 into A square sine alpha by alpha square cos square. The value of delta is pi E plus D sine theta by lambda. Let beta is equal to pi E plus D sine theta by lambda. The place substitute beta. That is called I is equal to R square is equal to 4 A square sine alpha by alpha square cos square beta. So here the two terms is there. A square sine alpha by alpha square, that is A sine alpha by alpha square is called diffraction phenomena. Cos square beta is called the interference phenomena. So the diffracted light of the double slit experiment in propagation of the light, both interference and diffraction is possible. From the above equation, it is clear that the resultant intensity is the product of the two factors. One is called A square sine square alpha by alpha square, represents diffraction due to single slit. Another one is cos square beta, which gives the interference pattern due to the wavelets from double slits. So the resultant intensity to the both the diffraction and interference effect. The first one is diffraction effect. In diffraction effect is the principal maxima condition, theta is equal to 0 and alpha is equal to 0. The minimum intensity condition, sin alpha is equal to 0, then is called alpha is equal plus or minus m pi. So this alpha is equal to E sin theta is equal plus or minus m pi. And secondary maxima is alpha is equal plus or minus 3 pi by 2, plus or minus 5 pi by 2, plus or minus 7 pi by 2, and so on. That is the values is representation. The interference pattern is the interference term. Cos square beta gives the equidistance, bright and dark fringes. The maximum intensity condition, the minimum intensity condition. The maximum will occur cos square beta is equal to 1, and beta is equal to plus or minus n pi. The beta is equal to pi e plus d sin theta by lambda is equal to plus or minus n pi. Both sides pi get cancelled, and e plus d sin theta is equal to plus or minus n lambda, where n is equal to 0, 1, 2, 3, and so on values. That is called the maxima condition or bright band condition. And minimum condition is e plus d beta is equal cos square beta is equal to 0, then beta is equal plus or minus 2n plus 1 pi by 2. So where n is equal to 0, 1, 2, 3, and so on values, e plus d sin theta is equal plus or minus 2n plus 1 lambda. That is n is equal to 0, 1, 2, 3, and so on values. So the intensity distribution curve is representation as. So this is called diffraction. This is called interference. Both combination of interference and diffraction is another diagram. So this is called intensity distribution curve. Another one is diffraction grating. In diffraction grating is already in laboratory point you have to do a laser grating, particle size by laser, and grating spectrum. These are the experiments done by the laboratories. And diffraction grating means it is a parallel slits. That is called D is called the width of the slit. E is called width of the line. E plus D is called a diffraction grating element, and transparent opaque spaces, ruled lines, etc. Diffraction grating is nothing but closed placed multiple slits. It consists of very large number narrow slits side by side separated by opaque spaces. The incident light is transmitted through the slits and blocked by opaque spaces. Such a grating is called transmission grating. An arrangement which consists of large number of parallel slits of the same width and separated by equal and opaque spaces is called diffraction grating. In diffraction grating, let small e is the width of the line and d is called width of the slit. Then e plus d is called grating element. Therefore, capital N is the number of lines per inches on the grating. Then n e plus d is equal to 1 inches is equal to 2.54 centimeters. Then e plus d is equal to 1 inches by capital N, that is equal to 2.54 by capital N centimeters. That is called grating element. And due to the above fact, the width of the slit is narrow and comparable to the wavelength of light. So this is called the grating spectrum. The grating spectrum is, it is a visual colors. The conditions to the principal maxima in a grating is given by e plus d sin theta is equal to n lambda. Sin theta by capital N is equal to small n into lambda. Then e plus d is equal to 1 by capital N. Lambda is equal to sin theta by small n into capital N. Then you will calculate the grating wavelength, different colors of wavelength. This is known as grating equation. From the grating equation, it is clear that the particular wavelength lambda, the angle of diffraction theta is incident for principal maxima of different orders. As the number of lines in a grating are large, the maximum appears as a short. The bright parallel lines and are the termed as spectral lines. So for the white light and for particular order of n, the light of different wavelength will be diffracted in different directions. The spectra of different orders are situated simultaneously on the side of zero order. So this is called the spectral lines are more and more disappeared as to go the higher orders. It is a n number of orders. So this is called the complete picture of the diffraction.